With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Hello students, let's start the question. Which one of the following complexes shows optical isomerism? So we have 4 coordination complexes given over here. One by one, we'll be analyzing them and we would be talking about whether they would show optical isomerism or not. Now, the very first thing which needs to be clear in our mind is that how do you detect or how do you identify optical isomerism in coordination complexes? Yes. So the very first thing is that, as the whole scenario goes, is that whenever we want to identify optical isomerism in coordination complexes, of course, the metal atom or the metal species should be surrounded by 4 different ligands, okay? 4 different ligands. And it should be having a chiral center, okay? This could be number 1 condition. But let me tell you one thing. In this case, this could be applicable in cases of a tetrahedral complex. Okay, what is it? The tetrahedral complex where the molecule is not planar. Yes, where the species is not planar, all those 4 ligands would be present in different planes. Yes, so that is what is one condition which we would be having. Yes, now the other condition would be in which we would be having the molecule or the species giving rise to a mirror image which is non-superimposable in nature. Okay, non-superimposable in nature. Now, what do you mean by this term? So supposedly if I'm having a particular coordination complex, something like maybe of the type, let me just draw it over here. So supposedly if it was showing me an octahedral complex, okay, I'm taking the example of an octahedral complex in which I'm having the same types of ligands which are adjacent to each other. Yes, in this manner, fine. And I want to say that I want to prove whether this is showing an optical isomerism phenomena or not. Now over here, no one is in transposition. Yes, all of them are they are adjacent to each other. Yeah, there is no plane of symmetry also. And in that case, what we do is draw the mirror image of this particular complex. Yes, so the ligands which are nearer would be written nearer. Yes, and the ones which are farther away would be written in this manner. Yes, and accordingly you put it up in this manner. Yes, now if you place this particular mirror image, okay, on the original molecule, okay, or the species, if at all it is having a positive or a negative charge. Yes, so you pick this up and you place it over here on this mirror image or on this original object whose mirror image we have drawn on the right. So on picking it up, you'll be able to see that your A ligand is being overlapped by the B ligand. The next A ligand has been overlapped by C. Yes. Then the B ligand has been overlapped by A and C is overlapped by A. Yes. B and C are totally common. Okay. So that would be the scenario. But the other ligands which are in the same plane are overlapping on different ligands, or other ways there are no same groups which are overlapping over each other. Yes. And that is what we call as non-superimposable mirror images. Are you getting my point? Yes. So in such cases, we name these isomers as enantiomers, and these 2 mirror images are the dextro and the levorotatory isomers of each other. Yes, and hence in that case we can say that optical isomerism or optical activity will be shown by this type of a structure. Yes, okay. Now, taking forth this concept, now let us analyze the given structures over here. Yes, so the first structure is a cis isomer of this cobalt, yes, wherein we are having En twice Cl2. Okay, fine. En twice Cl2 is in cis position. Cis position means it would be on the same side. Now, since this is an octahedral complex, since En is nothing but a bidentate ligand, okay, it will be having 2 points of attachment each. So there are 4 attachments coming from the ethylene diamine. Yes, that's En, and Cl2 will give me 2 points of attachment. So that's a total of 6, which is an octahedral complex, isn't it? So in that case, let us draw the cis isomer first. Okay. Now, while drawing the cis isomer, this is the way you could draw it. Yes, number 1, and the next one will be over here. That's your number 2 ethylene diamine ligand. I have shown the points of attachment, that is your nitrogen atoms, yes. And the other 2 Cl atoms would be placed over here. Yes. So this is your so-called cis isomer of the cobalt species given right away. Yeah. So let me show the ones which are in the square planar part in the same plane. Yes. So these are the 4 ones. Yes. Whereas these 2, that is this nitrogen of one of the ethylene diamine ligand and this chloro group is on, or otherwise they are in transposition to each other. Now in this case, if you can see well, we cannot have any kind of, if you go to see it very clearly, we would be able to see that there is no plane of symmetry as such. Okay. Now let us highlight it properly. Supposedly, if you were imagining to pass a plane of symmetry from this point. Yes. So on either sides of cobalt, on the upper side, I'm having nitrogen, ethylene group, nitrogen, nitrogen. Yes. And the ethylene group is being divided over here. Now on the other side, I'm having nitrogen and 2 chloro groups. So no, this doesn't count as a plane of symmetry, isn't it? Yes. Now let us pass it vertically. That is this way. Okay. So in this case, you're having the cutting of the nitrogen atom as well as chloro group. But on either sides, do you have the same ligands? No. Now, any one plane of symmetry you consider, whether it's from the diagonals or from any other location, you will not be able to find any plane of symmetry. In short, since there is no plane of symmetry, yes, since there is no plane of symmetry, we can definitely say that optical isomerism can exist. Yes, optical isomerism will exist. So there would be a mirror image of this one. Yes, and that will show me 2 optical isomers. Okay, optical isomerism will always show this D and L isomers. Okay, those would be the 2 for one structure. Yeah, so 2 optical isomers will be seen. So for sure, option number A is definitely showing us an optical isomerism existence. Yes, so this was your structure number 1. Now let us analyze structure number 2. It's the same structure, but it is in trans form. Okay, so this trans geometrical isomer will show its existence. So you would be having the ethylene diamine ligands in transposition. Yes, so let me show them in transposition. Say like the chloro group will be in this manner. Okay, let me show it in this manner. Whereas the ethylene diamine, let me show it in this manner. Yes. Perfect. Yes. Now, what next? Next is the analysis part. Yeah. So now let us look at this. Let us join the 4 atoms. Oh, I missed out on nitrogen over here. Sorry for that. Okay, and 1, 2, 3, and 4. So these are the 4 atoms which would be in one plane itself. Yes, and obviously chloro is in trans, as well as these nitrogen atoms are also in trans position. Now, in that case, let me just write trans. Yes. Now, in that case, definitely a plane of symmetry exists. How come? Let us see this. So if you're placing a plane of symmetry from this particular angle, from this particular point, you'll be seeing that on either sides of the plane, you're having the same number of ligands. Okay, fine. And even though this is the ethylene group, it is cutting into half. So it's on either sides. Yeah. Now, if you're placing the plane of symmetry from this point, that's a vertical one. Again, the same thing. It is dividing the molecule into 2 halves, as well as the diagonals are also doing the same. So in short, we can say that there is a plane of symmetry seen. Yes, there is a plane of symmetry seen, and hence there would not be any kind of optical isomerism. Yes, okay, fine. Now, moving on to the next structure. That's structure number 3. We are having CO NH3 Cl2 Cl. Yes. Now let us advance towards this structure. Now this structure is going to have 4 ammonia ligands. So what I'm going to do is I'm going to put them in this manner. Yes. And 2 Cl atoms in trans. Yes. Now let us look at this C. You join them, and again you do the same thing. You're going to let a plane of symmetry pass through any point. Yes, and that shows you the division of the molecule into 2 equal halves, isn't it? Yes. So definitely a plane of symmetry exists, and hence no optical isomerism would be seen, isn't it? Now what if I was exchanging this Cl, okay, this Cl by say maybe this NH3, okay, oh, I'm sorry, this Cl, let me exchange it, let me place it in adjacent position to the other Cl. Okay, so let me exchange these 2 groups, this ammonia and this chloro. So the structure would be in which all the other ligands, you keep them intact and only exchange the ones which we have decided for. Yes, so it's the chloro group coming over here. Both of them are happy, and here we go. So in short, what has happened is that you have 2 chloro groups residing on this side. Yes, 2 NH3 over here, these 2 NH3. Yes, let us join them. There we go. Yeah, and now let us analyze it. Now there was no plane of symmetry. There was a plane of symmetry existing in this compound, right? So in this form, definitely there was plane of symmetry. Yes. And hence, in that case, no optical isomerism. Okay. Now, what about this one? Let us find out for this one. So, let us imagine that we would be having a plane of symmetry passing from this particular point. Yes. And in that case, if you see, I'm having 2 NH3 ligands and 1 chloro group on this side of the plane, whereas 1 chloro and 2 NH3 ligands on this side. So which means that again we have got a plane of symmetry existing. Yes. So this one is true also for this form. Yeah. And hence in that case it means that optical isomerism will not be possible. Yes, not possible. Now comes the next structure for analysis. That's the last one. So option number 4, what do we have over there? We have CONH3Cl3. Okay, ready for this? Yes. So CONH3Cl3, NH3, So let us keep them on one side, something like the facial isomer, yeah. And here is your Cl. Okay, fine. I guess this side's NH3 went a little too down. So let me just put it in the right manner. Yes, and now we go. So in this case, these 4 ligands are going to be in the same plane. Perfect, yes. And now let us analyze it. So we are having 2 NH3 on this side, 2 Cl groups on this side, and these two groups, that is NH3 and Cl, above and below the plane. Perfect, yes. So definitely this is a facial isomer which we are seeing. But then in this case also, we can say that there is a plane of symmetry existing. How do you say that? So if you are looking at it from this point of view, where the plane of symmetry passes from this diagonal, there again we have a perfect plane of symmetry. In short, this particular group which is on that line of plane of symmetry, or that plane line, it would be cutting these ligands into half, so they would be equal on either sides. And we have 1 ammonia and 1 chloro group, 1 ammonia and 1 chloro group on either sides of the plane. So again, there is what? The plane of symmetry existence. Yes. So plane of symmetry exists. Yes. And hence there will not be optical isomerism. Okay. So in short, for this particular question and for the given options, we have already made our final answer. Yes. And that is your option number 1. That's your cis cobalt species, which is the only one which will be showing optical isomerism. I hope you understood the explanation. Thank you.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.